What is isolated power supplies and how does it function? An isolated power supply is a type of electrical power supply that separates the output power from the input power using electrical isolation. This isolation is typically achieved through the use of a transformer, which allows energy transfer via electromagnetic induction rather than a direct electrical connection. Key features of isolated power supplies. Electrical isolation is the separation of electrical circuits to prevent the flow of current between them while still allowing the transfer of energy or signals. This is typically achieved using physical barriers, such as air gaps or insulating materials, or through technologies like transformers and optoisolators. Key concepts of electrical isolation. No direct electrical connection. The circuits do not share a direct conductive path. Energy or signals are transferred using alternative methods like electromagnetic induction, optical signals, or capacitance. Safety. Protects users and equipment from high voltages or dangerous current leaks. Prevents electrical shocks and equipment damage in high voltage or sensitive applications. Noise immunity. Reduces the risk of electrical noise and interference affecting the operation of sensitive circuits, improving signal integrity. Elimination of ground loops. By isolating grounds, electrical isolation prevents the formation of ground loops, which can cause noise and erratic behavior in systems. Methods of electrical isolation. Transformers. Use electromagnetic induction to transfer energy between primary and secondary windings without a direct electrical connection. Widely used in power supplies, signal coupling, and voltage level conversion. Optoisolators. Optocoupler. Use light to transmit signals between isolated circuits. A light-emitting diode, LED, emits light, which is detected by a photosensitive component like a phototransistor. Capacitive coupling. Uses capacitors to transfer AC signals while blocking DC and providing isolation. Commonly used for high-frequency signal coupling. Magnetic coupling. In devices like isolators and transformers, energy is transferred via a magnetic field, maintaining isolation. Physical separation. In high-voltage systems, physical barriers, e.g., air gaps, insulating enclosures, ensure isolation between circuits. Applications of electrical isolation. Medical equipment. Protects patients from electrical shocks while ensuring safe operation of devices like ECGs and defibrillators. Industrial automation. Isolates control systems from high-power circuits to avoid interference and protect sensitive equipment. Telecommunications. Prevents noise and interference in communication systems by isolating data lines. Power supplies. In isolated power supplies, transformers provide electrical isolation between input and output circuits. Measurement and test equipment. Ensures accurate readings without introducing ground loops or disturbances. Key standards for electrical isolation. Creepage and clearance. Creepage. The shortest path along the surface of an insulating material. Clearance. The shortest air gap between two conductive parts. Adherence to these parameters ensures effective isolation. Dielectric strength. Measures the material's ability to withstand high voltage without breaking down. Isolation voltage ratings. Specifies the maximum voltage the isolation can handle without failure. Electrical isolation is critical in ensuring safety, reliability, and performance across a wide range of electronic and electrical systems. Safety in the context of electrical systems refers to practices, designs, and technologies that protect individuals, equipment, and the environment from harm caused by electrical hazards. Proper electrical safety minimizes risks such as electric shock, burns, fires, and explosions. Key aspects of electrical safety. Protection against electrical shock. Shock occurs when current flows through the human body. Prevention involves insulation, grounding, circuit isolation, and protective devices. Fire prevention. Electrical fires can result from overloaded circuits, short circuits, or faulty equipment. Safety measures include proper circuit design, overcurrent protection, e.g., fuses, circuit breakers, and regular equipment maintenance. Overload and short circuit protection. Overloads and short circuits can cause excessive current, leading to heat and potential damage. Devices like circuit breakers and fuses are used to interrupt the current flow in such conditions. Grounding, earthing, ensures that any fault current is safely directed to the ground, reducing the risk of shock and damage. Proper grounding is essential for system stability and user safety. Isolation. Electrical isolation prevents direct contact with high-voltage parts, reducing shock risk and protecting sensitive components. Personal protective equipment, PP, includes insulated gloves, safety shoes, goggles, and arc flash suits for those working on or near electrical systems. Compliance with standards. Adhering to safety standards like IEC, OSHA, and NFPA ensures that electrical systems meet rigorous safety criteria. Common electrical hazards. Electric shock can occur from direct contact with live wires or through faulty insulation. Severity depends on current, voltage, and duration of contact. Arc flash. A sudden discharge of electrical energy causing high heat, pressure, and light can result in severe burns or equipment damage. Overheating, caused by overloading or poor connections, leading to potential fires. Ground loops. Differences in ground potential can create unwanted currents, leading to shock risks and equipment malfunction. Safety measures. Design safety. Use proper insulation, enclosures, and components rated for the intended voltage and current. Include isolation transformers, circuit breakers, and protective relays. Proper installation. Follow established guidelines and codes, e.g., NEC, IEC. Ensure secure connections and proper grounding. Regular maintenance. Inspect and repair worn-out insulation, loose connections, and aged equipment. Test circuit protection devices periodically. Training and awareness. Educate personnel on electrical hazards and safe work practices. Train workers to identify and address risks before starting tasks. Use of detection systems. Install ground fault circuit interrupters, GFCIs, to detect and stop leakage currents. Use monitoring systems to track potential faults. Standards and regulations. National Fire Protection Association, NFPA, NFPA 70, National Electrical Code, sets guidelines for safe electrical installations. Occupational Safety and Health Administration, OSHA enforces workplace safety regulations. International Electrotechnical Commission, IEC, sets global electrical safety standards. By combining engineering practices, regular inspections, and proper training, electrical safety ensures reliable operation and minimizes risks to people and property. Noise reduction in electrical and electronic systems refers to minimizing or eliminating unwanted electrical signals, noise, that can interfere with the desired operation of circuits and devices. Noise can originate from various sources, including external electromagnetic interference, EMI, or internal circuit behavior. Effective noise reduction ensures reliable performance, improves signal integrity, and prevents errors in sensitive systems. Sources of noise. Electromagnetic interference, EMI, radiated noise from external sources like motors, transformers, or radio waves. Conducted noise traveling through power lines or signal cables. Switching noise, generated by rapid transitions in switching circuits, such as in power supplies or digital devices. Thermal noise, caused by the random motion of electrons in resistors, transistors, and other components. Ground loops occur when different parts of a system share multiple ground connections, creating unwanted currents. Crosstalk, signal leakage between adjacent wires or traces. Noise reduction techniques. Shielding, use conductive enclosures or cables with metallic shielding to block radiated noise. Examples: coaxial cables, shielded twisted pair wires. Grounding, ensure proper grounding to prevent ground loops. Use a single-point ground or ground plane in circuit designs. Filtering, use filters to block unwanted frequencies. Low-pass, high-pass, or bandpass filters are applied based on the frequency range of the noise. Decoupling capacitors, placed across power supply lines to smooth voltage fluctuations, helps stabilize supply voltage and reduce switching noise. Twisted pair cables, twisting wires reduces susceptibility to EMI by canceling out interference. Proper PCB layout, separate high-frequency and low-frequency components. Minimize trace lengths and avoid running signal lines parallel to each other. Isolation, use transformers or optoisolators to electrically isolate noisy circuits from sensitive ones. Power conditioning, Use line filters or uninterruptible power supplies, UPS, to remove noise from incoming power. Damping components. Add resistors, ferrite beads, or inductors to reduce high-frequency oscillations. Balance signals. Differential signaling, like in Ethernet or USB, cancels out common mode noise. Applications of noise reduction. Communication systems. Reduces signal degradation in wired and wireless systems, ensuring clear data transmission. Medical devices. Eliminates noise to ensure accurate readings in sensitive equipment like ECG machines. Audio and video systems. Prevents hums, buzzes, and interference for better sound and picture quality. Industrial equipment. Protects control systems and sensors in noisy environments. Power electronics. Mitigates switching noise in converters and inverters. Advanced noise reduction techniques. Active noise cancellation. Uses real-time processing to generate anti-noise signals that cancel out the original noise. Spread spectrum techniques. Spreads the energy of a noise signal across a wider frequency range, reducing its impact on specific frequencies. Digital signal processing, DSP. Filters and processes signals in digital domains to remove noise without affecting the desired signal. By implementing these techniques, designers can ensure robust, reliable, and noise-free operation of electronic systems. Flexibility in electrical and electronic systems refers to the capability of a system to adapt to different requirements, configurations, or environments without significant changes to its design or performance. This quality is especially important in modern systems, where adaptability to varying operational needs and integration with diverse components are key factors for efficiency and reliability. Aspects of flexibility in electrical systems. Scalability. Systems can be scaled up or down in capacity, e.g., power supplies handling different loads. Modular designs allow easy addition or removal of components. Multi-voltage compatibility. Supports a range of input and output voltage levels, enabling operation across various devices and regions. Common in universal power supplies and multi-voltage systems. Adaptability to different environments. Designed to work in various environmental conditions, such as temperature extremes, humidity, or high vibration areas. Example, rugged industrial equipment or outdoor power solutions. Integration with diverse systems. Ability to interface with different protocols, standards, or architectures. Examples include universal serial bus, USB, standards, and Ethernet powered devices. Customizable output. Adjustable parameters like voltage, current, or frequency to suit specific applications. Variable frequency drives, VFDs, are examples of devices with customizable outputs. Support for redundant systems. Redundancy ensures continuous operation in case of failure, improving reliability. Dual power supplies or parallel configurations enhance flexibility for critical systems. Examples of flexible systems. Isolated power supplies. Offer flexibility by allowing multiple independent outputs, each with its own ground potential. Useful in applications requiring different voltage levels or isolated circuits. Programmable logic controllers, PLCs. Highly flexible for automation tasks, as they can be reprogrammed for various processes. Easily integrate with new sensors, actuators, or communication protocols. Smart grids. Adapt to varying energy demands, integrate renewable sources, and manage distributed loads dynamically. Universal chargers. Provide compatibility with various devices by supporting multiple output voltage levels and connector types. Power distribution units, PDU. Flexible designs allow for dynamic load balancing, surge protection, and multi-outlet configurations. Advantages of flexibility. Cost efficiency. Reduces the need for redesigns or specialized components, lowering production and operational costs. Improved usability. Simplifies operation and maintenance, as systems can adapt to a wide range of scenarios. Future-proofing. Systems can accommodate evolving technologies or standards without requiring major overhauls. Enhanced reliability. Redundancy and adaptability to varying loads or environments improve overall system resilience. Designing for flexibility. Modular architecture. Break systems into interchangeable modules that can be upgraded or replaced independently. Wide input and output range. Design circuits and power systems with broad operating ranges. Standardized interfaces. Use industry-standard connectors and communication protocols to ensure compatibility. User configurability. Provide options for users to modify settings, such as programmable voltage regulators or multimode devices. Applications requiring flexibility. Consumer electronics. Devices like universal adapters and multifunctional gadgets demand adaptability. Industrial automation. Systems need to accommodate diverse sensors, machines, and operational parameters. Telecommunications. Networks must handle varying bandwidth, power levels, and redundancy requirements. Renewable energy systems must integrate with grids, batteries, and variable power sources like solar or wind. Flexibility ensures that electrical and electronic systems remain versatile, robust, and efficient in a rapidly changing technological landscape. How it works. AC input refers to alternating current, AC, power supplied to an electrical or electronic device, typically from a mains power source, e.g., wall outlets. AC input is widely used for powering systems because of its efficient long-distance transmission and compatibility with common electrical infrastructure. Characteristics of AC input. Alternating nature. The voltage and current periodically reverse direction. In most regions, the frequency is 50 Hz, e.g., Europe, or 60 Hz, e.g., North America. Voltage levels. Standard mains voltage varies by region. 110, 120 V in countries like the United States and Japan. 220, 240 V in Europe, Asia, and other regions. Sine wave. The AC waveform is typically sinusoidal, providing smooth power delivery. Common applications of AC input. Power supplies. Converts AC to DC using rectifiers, transformers, and filters to power electronic devices. Examples: computers, televisions, and battery chargers. Electric motors. AC input directly powers motors for appliances, fans, and industrial machinery. Lighting systems. Supplies power for incandescent, fluorescent, and LED lighting. Heating systems. AC input powers resistive heating elements in devices like ovens and water heaters. Components in an AC input system. Transformer. Steps up or steps down the AC voltage to match the required input for a device. Rectifier. Converts AC to DC for devices that operate on direct current. Filters. Smooths out the rectified voltage to reduce ripples and noise. Surge protection. Protects devices from voltage spikes or transients. Power factor correction, PFC. Improves the efficiency of AC input systems by aligning voltage and current phases. Advantages of AC input. Efficiency in transmission. AC power can be easily transmitted over long distances using transformers to adjust voltage levels. Compatibility. Most homes, industries, and commercial establishments use AC power for standardization. Ease of conversion. AC can be converted to different voltage levels or to DC as needed. Challenges of AC input. Voltage fluctuations. Variations in mains voltage can affect device performance or cause damage without proper regulation. Electromagnetic interference, EMI. AC signals can generate EMI, affecting nearby sensitive equipment. Energy loss. Some power is lost in heat generation during transmission and conversion processes. Modern innovations with AC input. Switching power supplies. More efficient AC to DC conversion using high-frequency switching. Smart grids. Optimized delivery of AC power with real-time monitoring and control. Universal AC input. Devices designed to accept a wide range of AC input voltages, e.g., 90, 264 V, for global compatibility. AC input remains a fundamental power source for countless devices, systems, and applications, offering versatility, reliability, and compatibility with existing infrastructure. DC input refers to the supply of direct current, DC, power to a device or system. Unlike alternating current, AC, DC power flows in a single, constant direction with a fixed polarity, positive and negative terminals. DC input is commonly used in electronic devices and systems that require stable and precise power delivery. Characteristics of DC input. Unidirectional flow. Current flows in one direction, making it ideal for powering circuits that need consistent voltage levels. Voltage stability. Provides a constant voltage, e.g., 5V, 12V, or 24V, ensuring steady operation of sensitive electronics. Polarity sensitive. Devices typically require correct polarity for proper operation. Reversed polarity can damage the equipment. Common sources of DC input. Batteries. Portable and reliable DC sources, commonly used in mobile devices, remote systems, and vehicles. Power supplies. AC to DC converters provide DC input for devices like computers, routers, and audio systems. Solar panels. Produce DC power directly, used in renewable energy applications. DC generators. Generate DC power for industrial and backup systems. Applications of DC input. Electronics. Powers devices like smartphones, laptops, and LED lighting systems. Industrial control systems. DC inputs drive programmable logic controllers, PLCs, sensors, and actuators. Telecommunications. Provide stable power for networking equipment, base stations, and data centers. Electric vehicles, EV. Batteries supply DC power for motors and control systems. Components in a DC input system. Voltage regulators. Ensure stable voltage output to protect sensitive components. Filters. Smooth out any residual noise or ripples in the DC signal. Polarity protection. Diodes or circuits protect against incorrect polarity connections. DC-DC converters. Step up or step down DC voltage to the required level. Advantages of DC input. Stability. Provides a constant voltage, ideal for sensitive electronics. Efficiency. Minimal power loss during transmission over short distances. Compatibility with renewable energy. Works seamlessly with solar panels and batteries. Simple integration. Easy to use with modern electronic circuits and systems. Challenges of DC input. Voltage drop. Over long distances, DC power can experience significant losses without proper cabling. Conversion requirements. Many applications require DC to be generated from AC power, adding conversion complexity. Limited transmission. DC is less efficient than AC for long-distance power distribution. Modern innovations in DC input. Universal DC chargers. Devices like USB-C offer standardized DC power delivery for various devices. High-efficiency DC-DC converters. Advanced converters optimize power delivery for applications like robotics and EVs. Microgrids. Localized DC power networks efficiently integrate renewable energy and battery storage. DC input is vital in powering modern electronics, renewable energy systems, and many industrial applications due to its stability, efficiency, and compatibility with low-voltage systems. Rectification and filtering are key processes in converting alternating current, AC, to direct current, DC. These steps are essential in power supply systems, enabling smooth and stable DC output required by most electronic devices. 1. Rectification. Rectification is the process of converting AC, which periodically reverses direction, into DC, which flows in one direction. It is performed using diodes or rectifiers that allow current to flow in only one direction. Types of rectification. Half-wave rectification. Uses a single diode. Allows only one half of the AC cycle, positive or negative, to pass through. Simple but inefficient, as half of the input AC signal is blocked. Output. Pulsating DC with gaps between cycles. Full-wave rectification. Utilizes two diodes with a center-tap transformer or a bridge rectifier with four diodes. Both halves of the AC cycle are used by inverting the negative half to positive. More efficient and produces smoother output compared to half-wave rectification. Output. Continuous pulsating DC. Bridge rectifier. A type of full-wave rectification using four diodes arranged in a bridge configuration. Does not require a center-tap transformer, making it more compact and widely used. 2. Filtering. Filtering smooths the pulsating DC produced by the rectification process, reducing ripples and delivering a more stable DC output. Types of filters. Capacitor filter. A capacitor is placed parallel to the load. It charges during the peak of the waveform and discharges during the dips, filling gaps in the rectified signal. Advantage: simple and effective for low ripple reduction. Limitation: ripple increases with higher loads due to faster capacitor discharge. Inductor filter. An inductor is placed in series with the load. It resists changes in current, smoothing the ripple. Advantage: effective for high current loads. Limitation: bulky and costly. LC filter, inductor capacitor, combines an inductor and a capacitor to smooth both voltage and current. Advantage: high filtering efficiency. Limitation: complex and expensive. RC filter, resistor capacitor, uses a resistor and capacitor in series parallel configuration. Simple and cost-effective for light loads. Voltage regulators, used after the filtering stage to provide a stable and constant output voltage regardless of input fluctuations or load changes. Combined process, rectification and filtering. Input AC signal. The system starts with an AC signal from the mains or a transformer. Rectification. A diode rectifier converts the AC signal into pulsating DC. Filtering. A filter smooths the pulsating DC to reduce ripples. Output. The result is a steady DC voltage suitable for powering electronic devices. Applications. Power supplies, used in computers, chargers, and industrial equipment to convert AC to DC. Battery charging, provides a steady DC voltage for charging batteries. Signal processing. Rectification is used to detect and process AC signals in communication systems. DC motors and LEDs. Both require smooth DC power for operation, making rectification and filtering essential. Advantages of rectification and filtering. Converts AC to DC efficiently. Provides steady and stable voltage for sensitive electronic components. Ensures reliable performance in devices by minimizing ripple and noise. By combining rectification and filtering techniques, electrical systems can deliver clean DC power, ensuring compatibility with modern electronic devices and systems. Regulation in electrical and electronic systems refers to maintaining a consistent and stable output voltage or current, regardless of variations in input supply, load conditions, or environmental factors. This is a critical function for ensuring reliable operation and protecting sensitive electronic components. Types of regulation. Voltage regulation ensures that the output voltage remains constant despite changes in input voltage or load. Used in power supplies, voltage stabilizers, and electronic circuits. Current regulation maintains a constant output current regardless of load resistance or supply fluctuations. Essential in applications like LED drivers and battery chargers. Need for regulation. Protecting devices. Prevents damage to sensitive components caused by voltage spikes or drops. Ensuring stable operation. Provides a consistent operating environment for electronic devices. Minimizing noise and ripple. Reduces disturbances in power supplies, improving performance. Compensating for variations. Handles changes in input power, e.g., mains voltage fluctuations, and load conditions, e.g., varying current demands. Methods of regulation. 1. Linear regulators. Uses a voltage control element, like a transistor, to maintain a constant output voltage. Excess energy is dissipated as heat. Advantages: simple design, low noise and ripple. Disadvantages: inefficient, especially at high voltage differences. Generates significant heat. Example: 78XX series regulators, e.g., 7805 for 5V output. 2. Switching regulators. Uses high-frequency switching and energy storage components, inductors, and capacitors to regulate output voltage. More efficient than linear regulators. Types: step-down, buck, regulator. Converts a higher input voltage to a lower output voltage. Step-up, boost, regulator. Converts a lower input voltage to a higher output voltage. Buck-boost regulator. Can increase or decrease voltage depending on input-output requirements. Advantages: high efficiency. Can handle a wide range of input and output voltages. Disadvantages: more complex design. generates more noise than linear regulators. 3. Feedback-based regulation. Monitors the output using a feedback loop to adjust the regulator's performance dynamically. Common in both linear and switching regulators. Components. Voltage reference, e.g., Zener diode or bandgap reference. Error amplifier to compare output with the reference. Control element, e.g., transistor or MOSFET. 4. Digital regulation. Uses microcontrollers or digital signal processors, DSPs, to regulate output parameters. Allows for programmable control and advanced features like monitoring and fault protection. Advantages: highly precise, flexible, and adaptable to different requirements. Key parameters for regulation. Line regulation measures the regulator's ability to maintain output despite changes in input voltage, expressed as a percentage or in volts. Formula: line regulation equals delta. Delta. Line regulation equals delta V in, delta V out. Load regulation measures the regulator's ability to maintain output under varying load conditions, expressed as a percentage or in volts. Formula: load regulation equals minus load regulation equals V out full load, V out no load, minus V out full load. Efficiency indicates how much input power is converted to useful output power. High efficiency is critical in minimizing energy loss and heat generation. Formula: efficiency equals times 100%. Efficiency equals P in, P out times 100%. Applications of regulation. Power supplies. Ensures stable DC output for electronics. Battery chargers. Provides controlled current and voltage for safe charging. Communication systems. Stabilizes power for signal integrity in sensitive equipment. LED drivers. Maintains constant current for uniform brightness and longevity. Automotive systems. Regulates voltage in vehicles to power various subsystems. Advantages of regulation. Stability. Provides consistent operation of electronic devices. Protection. Guards against overvoltage, undervoltage, and load variations. Efficiency. Minimizes power losses in advanced designs. Versatility. Supports a wide range of applications, from consumer electronics to industrial systems. Regulation is a cornerstone of modern electrical and electronic design, ensuring that devices operate safely, efficiently, and reliably in diverse conditions. Advantages of isolated power supplies. An isolated power supply uses a transformer to separate the input and output circuits electrically. This isolation offers numerous benefits, particularly in safety, performance, and versatility. Below are the key advantages. 1. Electrical isolation. Safety. The transformer separates the primary, input, and secondary, output sides, protecting users and connected devices from electrical faults such as short circuits or overvoltages. Eliminates ground loops. Isolation prevents unwanted ground loops, which can introduce noise or cause erratic behavior in sensitive equipment. 2. Noise reduction. Reduced interference. Isolation minimizes the transfer of electrical noise from the input to the output, improving the performance of sensitive devices like medical equipment and audio systems. Improved signal integrity. By breaking direct electrical connection, isolated power supplies reduce high-frequency noise and ripple. 3. Enhanced safety. Shock protection. Isolation prevents the output from being directly connected to the high-voltage input, reducing the risk of electric shock. Fault containment. In the event of an input side fault, the isolation barrier limits its effect on the output side. 4. Voltage compatibility. Multiple voltage outputs. Isolated power supplies can produce multiple independent output voltages from a single input source, useful for powering different circuits with distinct requirements. High voltage applications. Often used in systems where the input and output operate at significantly different voltage levels. 5. Flexibility and versatility. Supports diverse applications. Isolation allows the power supply to work with various systems, including medical devices, industrial machinery, telecommunications, and renewable energy setups. Customizable outputs. Outputs can be tailored to meet specific voltage and current requirements while maintaining electrical isolation. 6. Improved reliability. Fault isolation prevents input side issues, e.g., spikes, surges, from affecting downstream components, extending their operational lifespan. Enhanced durability. By isolating high-power or noisy input sources, the system minimizes wear and tear on sensitive electronic parts. 7. Compliance with safety standards. Isolated power supplies are often required in applications subject to strict safety and regulatory standards, such as medical devices must meet IEC 60601 standards for patient safety. Industrial control systems requires isolation for robust performance and safety. Telecommunication equipment adheres to industry standards for noise immunity and safety. 8. Energy efficiency. Modern isolated power supplies, such as switch-mode power supplies, SMPS, achieve high efficiency due to advancements in transformer design and switching technologies. 9. Protection against electromagnetic interference, EMI. Isolation reduces the risk of EMI affecting the output voltage, which is crucial in environments with high electrical noise, such as factories or medical facilities. 10. Scalability. Isolated power supplies are modular and can easily be scaled for systems requiring multiple isolated outputs. Applications of isolated power supplies. Medical equipment ensures patient safety by isolating the equipment from the main supply. Industrial automation powers sensors, actuators, and controllers without interference. Telecommunications provides stable power to sensitive networking equipment. Renewable energy systems ensures safe and efficient power conversion in solar inverters or wind turbines. Consumer electronics powers devices with multiple independent circuits or sensitive audio systems. Summary: isolated power supplies offer superior safety, noise immunity, and flexibility, making them indispensable in applications requiring high performance, reliability, and compliance with stringent safety standards. Isolated power supplies are widely used in various industries and applications where safety, noise reduction, and system stability are critical. Below are some of the common applications of isolated power supplies. 1. Medical equipment. Safety. Medical devices often require isolated power supplies to protect both the user and the patient from electrical shocks. Isolation helps meet stringent safety standards like IEC 60601. Examples: patient monitors, defibrillators, imaging systems, e.g., MRI, CT scanners, and diagnostic equipment. 2. Industrial control systems. Protection. Isolated power supplies are essential in industrial automation to protect control systems, sensors, and actuators from electrical faults or power surges. Examples: programmable logic controllers, PLCs, robots, motor controllers, and industrial sensors. 3. Telecommunications equipment. Noise immunity. Isolated power supplies provide stable and noise-free power to critical telecommunications equipment, which must function reliably even in environments with high electromagnetic interference, EMI. Examples: networking equipment, routers, switches, base stations, and communication relay systems. 4. Audio and video equipment. Reduced interference. Audio systems, especially in professional environments, require isolated power supplies to minimize noise and hum. This ensures high-quality sound performance. Examples: audio amplifiers, mixing consoles, professional microphones, and video cameras. 5. Renewable energy systems. Efficiency and safety. In solar power systems, wind turbines, and other renewable energy sources, isolation ensures the safe conversion and distribution of power. It also minimizes power losses. Examples: solar inverters, wind turbine controllers, and battery charging systems. 6. Consumer electronics. Multiple outputs. Many modern consumer electronic devices require isolated power supplies to power multiple circuits from a single input source while protecting sensitive components. Examples: power adapters for laptops, electric vehicles, EV, chargers, LED lighting systems, and home entertainment devices. 7. Electric vehicles, EVs. High voltage isolation. EV power systems require isolation to ensure safety when charging and during communication between different electrical components, e.g., motor control, battery management. Examples: EV chargers, battery management systems, and power inverters. 8. Power supply units for computers. Protection and reliability. Computer power supplies often use isolation to prevent electrical faults from damaging sensitive internal components. Examples: desktop and server power supplies, uninterruptible power supplies, UPS, and rack-mounted power systems. 9. Aerospace and defense. Robustness and safety. Isolated power supplies are used in aerospace applications for ensuring electrical safety and system stability in high-reliability environments. Examples: satellite systems, flight control systems, radar, and communication systems. 10. Test and measurement equipment. Accurate readings. Many test and measurement devices use isolated power supplies to avoid interference and noise from external power sources. This is important for precision and accuracy. Examples: oscilloscopes, signal generators, and power analyzers. 11. Automotive and electric propulsion systems. System protection. Isolation ensures that electrical systems in vehicles, such as electric drivetrains, sensors, and battery management systems, operate safely and efficiently. Examples: electric vehicle powertrain controllers, hybrid vehicle systems, and automotive testing equipment. 12. Military applications. High safety standards. Isolated power supplies are crucial in military electronics to ensure operational safety and reliability under extreme conditions. Examples: communication systems, radars, surveillance equipment, and control systems in military vehicles. 13. Laboratory equipment. Precise control. Isolated power supplies are used in laboratory instruments to protect delicate devices from electrical surges and to provide precise, stable power for experiments and measurements. Examples: power supplies for scientific instruments, research labs, and testing facilities. 14. Data centers. Continuous operation. Isolated power supplies ensure that servers, routers, and other networking equipment continue to operate even when the input power is unstable. Examples: UPS systems, server power supplies, and backup power solutions for data centers. 15. Heating, ventilation, and air conditioning, HVAC systems. System protection. Isolated power supplies are used in HVAC systems to protect the control and monitoring systems from power surges, ensuring smooth operation. Examples: HVAC controllers, temperature sensors, and air conditioning system monitors. 16. High-voltage equipment. Safety in high-voltage applications. For systems that operate at high voltages, isolation ensures that any faults or surges on the high-voltage side do not affect low-voltage circuits. Examples: high-voltage power transmission systems, medical equipment like X-ray machines, and industrial electrical systems. Summary: isolated power supplies are used in a wide range of applications, particularly where safety, noise reduction, and system stability are paramount. Whether it's protecting sensitive medical devices, ensuring reliability in telecommunications, or powering complex industrial machinery, isolation plays a crucial role in safeguarding equipment and improving performance.